Good morning, everybody. I'm going to talk this morning about gel filtration. And it's like many techniques, it often has a number of different names that you can use. We've got gel filtration, we've got gel permeation chromatography, we've got size exclusion chromatography, and actually size exclusion chromatography is my preferred description for it because it is actually quite descriptive in terms of what you do. But what we'd like to do this morning is we're actually going to put gel permeation chromatography in the context of other chromatography. And then what I'm going to do is I'm going to describe the separation process in terms of elution volume. And what we're going to do is we're going to be able to characterize something called a partition coefficient. And from that partition coefficient, we're actually going to, it's called KAV, we're going to actually calibrate a column, pretty much like what you can see in front of you here, in terms of running standards on that column. And if we can actually run a number of standards, we can plot a graph of which actually allows us to have log concentration against KAV, and then when you actually run an unknown sample, then you can actually get a molecular weight from it. So that's pretty much the process that we're going to go through. And then towards the end of the lecture, I'll actually talk about some of the factors that we have to think about in terms of optimizing the process. Okay, so chromatography. This is just a general introduction to chromatography, some of the really important points that you need to be familiar with. And then what we'll do is we'll actually port that understanding across into the field of GPC, gel permeation chromatography. Okay, so probably everyone here is familiar with the concept and the separation process that's chromatography. Would that be reasonable to? Okay. So what I'm going to do here is we've got something in this representation here we'll call a wool-coated open tubular. Okay, this is the basic, most simplest form of chromatography that we can actually work with. And when we're talking about chromatography, of course, what we really want to do is we want to take a complex mixture, which I've represented in a binary form here, two different types of molecule. We're actually going to make an injection onto the front end of the column. We've got mobile phase passing along the column, and we have a stationary phase. Okay, now these principles are in every type of chromatography. And what we've actually got is we've got a situation where we have longitudinal mass transfer, we've got radial mass transfer or diffusion, and we try and strike a balance between those two processes. Because if you actually consider it, what we want to do is we want our molecules, which are at this point, we need them to somehow get to the surface, to interact with the stationary phase, and it's only when you interact with the stationary phase can you actually hope to separate two molecules. Now, if you actually think about just two molecules, a binary mixture, each of the molecules have got something called a separation vector. Okay, and in GPC, that separation vector is size and shape. In lots of other types of chromatography, it could be a certain chemistry, a physical chemical process which actually allows it to interact with the stationary phase. And what we're really interested in is we're interested in that dynamics, the dynamics of interaction between a molecule and the stationary phase. And in this little figure here, I've tried to represent that process. And what it will allow me to do is allow me to introduce this partition coefficient, which is fundamental to all chromatography, and also the concept of theoretical plates. So this is our stationary phase. We have two molecules, similar molecules. One of them, for example, may actually want to partition into the stationary phase. And that is the ratio of molecules in this form as opposed to this form is represented by this partition coefficient. And this partition coefficient is fundamental to everything that we're going to talk about today. But equally, there could be another molecule adjacent to it which doesn't actually go into the stationary phase and isn't retained, but will continue down the column. And then at some point later on, it will actually interact with the stationary phase, and you can see this equilibrium going on. So this is basically what happens. The more theoretical plates you have, the more of these equilibria processes that you've go on, the greater the chance you've actually got a differentiating between molecules. Because the molecules can be quite subtly different. So you need lots of these interactions to actually go on. So if I move further down on this figure, we've got another molecule depicted by the red coloration. It's got a different partition coefficient, and the very fact that this one is actually further down the column should suggest to you that it is interacting to a lower degree with the stationary phase. It prefers to be more in the mobile phase in the stationary phase, and therefore it's moved past down the column more quickly. So just going back to this representation here, very simple thing with chromatography. We want to take a mixture in a concentrated form. We want to move it down the column. We're trying to strike a balance between the rate at which it's moving this way and the amount of radial diffusion and interaction with the stationary phase. But at some point it will actually come out the end of your column, and we will have a situation represented by this little schematic here where we've got two separate species that have been fractionated, separated, and then they can go through the process of detection. Now, detection is an absolutely fundamental thing. There's a whole series of detectors that are possible to you, and you've seen some of them this morning when Steve showed you through the SecMail system that we got. And we'll talk a little bit more about detection later. But that's basically the fundamental process that actually goes on in terms of chromatography. So now what we want to do is we just want to take those concepts and then move them into what we're talking about this morning, which is gel permeation chromatography or gel filtration. Great. So what I have here is another schematic, as we've shown previously, and what we've actually got here, we have our column, which instead of being wall-coated open tubular is now a collection of individual spherical particles. And those particles are actually packed into this column, and what we'd really like to do is we'd like to arrange for those porous beads, as it's depicted here, to actually be hexagonally close packed together. So what we would have is that we would have a situation, if you actually really focus down where the arrow is, I'm pointing at the moment, between these particles is an interstitial volume. And it is through that interstitial volume that your mobile phase passes. And what we would like is we would like this to be a nice homogeneous collection of particles, so we actually have some control of the flow that goes through our column. It's a nice uniform flow through the whole column. But basically what we've got, if we actually focus on this interstitial space here, we've got flow coming right in that point there, and it's interaction with the gel beads in a similar way that I depicted previously with wall-coated open tubular column. The difference here is that now what we've got our particle here, we've got a particular pore available to it, and we get this distribution, this partition. Small molecules can actually gain access to these little pores, and if they do, they are retained, because don't forget, the mobile phase is passing along this way. It will come into here, just like we talked about before. It's retained based on size and shape, not on some physicochemical process, just on size and shape. And as it says in big letters down at the bottom, if you actually think about it, large molecules can't get access to these pores and therefore stay in the mobile phase and just go through the column and are detected first. Small molecules actually have the ability to actually enter into these pores, and the smallest ones that have total access to this, okay, will be retained the most. And then we've got a whole range of molecules in between those two, where this distribution partition coefficient becomes operative, or becomes the description of the process. And that's really what we want to talk about now. We're going to talk about this KD value, the partition coefficient. And in fact, what we're going to develop now in the next couple of slides is the column parameters in volume terms, but we're actually going to develop something called a KAV, or K average, and this will be an average partition coefficient, and I'll talk a little bit more about that in a second. Okay, I suppose the other thing that I would like to say about this is that if we have hexagonally close packed spheres, which is what we're heading for, basically the smaller the particle we have, the smaller the channel between them that the molecules are flowing through, the greater the interaction we've got with the particle itself. So the smaller the particle, the more efficient we've got in terms of the interaction with the pores, and the greater the resolution that we can get in terms of separating molecules. The problem that we've got, the smaller the particle, the smaller the channel between them, the higher the pressure that you need to use. Okay, and we've got a couple of different types of chromatography. We've got a couple of different columns down here. I'll talk about those in a while, but basically the difference between them is particle size. Okay, so I think what I'd like to talk about now is just some of the parameters or properties that are relevant to doing GPC. And one of the things that we want to do, as I think I said earlier, is we want to take a nice sharp peak like this. We want it to be able to, which is approximating to our injection, we want to put it into a column, and what we want to do is we want it to interact with all the particles, and we would like it to come out in a similar form but separated from a molecule that is similar. But what we've actually got is we've got, in a representation like this, we've got the concept of peak broadening. Now, peak broadening is a problem for chromatographers, because basically what it does is, rather than the peaks being nice and sharp and separate, then their mean might be the same, but if they're in actually a very broad form like this, then you can't actually differentiate between them. What they become is unresolved. You have low resolution. So there's a couple of processes that actually go on here. For example, it could actually take a very straight path through your bed, or it could take a more tortuous route through the bed, and those two processes actually cause peak broadening, and peak broadening is something that we really don't want. Okay, so as I said, based on the partition process, that's an inherent mechanism for peak broadening. Another mechanism is something like this, different path length. Probably the worst type is if you don't have, if you have any channeling in your beads. If your beads aren't hexagonally close packed and you've got void volumes in there, then stationary flow will go through those, and they are actually called broadening. So broadening is something that we try to minimise as much as we can. Okay, so now what I'm going to do is just going to spend a little bit of time about talking about the actual phase itself. I mean, everything I've given you so far has been based on a schematic form, but if you actually did some SEMs of some of this PVA material, which is actually what the beads are made of in this instant, then rather than seeing nice schematic pores, which are very clear to understand, we actually see a bit of a heterogeneous surface composition. But each one of these effectively starts to behave like a pore. So this is actually really what we're working out. And when you actually work with bead material for large polymers, large molecular weights, then what we actually do is they actually manufacture these things by agglomerating microspheres. And if you can see them on this edge, they're tiny little spheres. And this is the mechanism that you actually go to make these beads. Now, so that's a nice way of visualizing actually what you've got. One of the big problems that you have with that, each one of those little microbeads can actually be released from the surface. And because we're doing light scattering, on many occasions when we're working in the NCMH, that actually produces a background noise, which is a big problem. And this really comes into play when you're actually working with big biomolecules, which in the polysaccharide fields that we work with, we are. So this is a bit of a problem for that. If you've got smaller molecules, it's less of a problem because you're using slightly different technologies in order to create your microspheres, your particles. Okay, so the next slide is just a very simple representation of what I've talked about previously this morning. Basically what I'm going to do is we put a mixture on the top of the column here. We have flow coming down here. Some is retained to a much greater degree than others. So this material has less access to the particle, to the pores, and will come out first. And then behind that we have the smaller molecules which are retained to a greater degree, and we get some form of a chromatogram as a function of retention time. So in the lab this morning, you've actually seen our SECMAL system, which was depicted on the right here. And I think Steve basically just relayed that to you. But effectively, we have a sample. We have a pump here, which actually generates our flow. It picks up our sample here. We make an injection on the bottom of the column. It flows through the column, is separated, and then goes through a detection stack. That's pretty much the system that we're using. So this column here is one that has got large particles in it. It's one which we can actually make an injection probably that way up. We can make an injection on the top of the column. We have liquid flowing through it, and it can be just gravity fed. It can just drip out through the bottom here. But basically what happens is we'll have our interaction going through the column here, and it will they'll slowly separate and come out the bottom. When we work with better come back to the camera. When we're working with a high pressure system, slightly more efficient form of chromatography, that's the form of the column that we're using. Okay, much smaller particles, much higher pressure. And what we tend to do, if you actually have a look at our working system, rather than just have a single analytical column, we have firstly a guard column, which stops any contaminants going into our analytical columns. And because the nature of chromatography, we probably need 2 analytical columns in order to cope with quite a wide range of molecular weights. So, you know, one of these columns would be for high molecular weight, one would be for lower molecular weight, and you can put them in together in series, and you can make it a broad range technique. Okay, so now what we're going to do, we're going to develop a few equations, very simple equations, which allow us to actually describe GPC in terms of elution volumes. And we've got a couple of schematics here, a couple of terms that I need to define for you, but we're heading towards being able to come up with an equation for the partition coefficient. So firstly, what we've got in this representation here, we've got the void volume. So this is the interstitial volume, not including the particles. Then we've got a total volume for the system. So is it represented there? That's the volume that's inside the particles and in the interstitial region. And then we've got this term Vs, which is actually the volume of the liquid that's actually held in the particle itself. Now what we actually do is we make an approximation, because it's very difficult to actually work out exactly what the volume in the particles is, because obviously the particle material, although it's only a small part, the structure of the particle, what creates the pores, has a finite volume. But in this approximation, we're going to say we're going to not take that into account, and we're just basically going to say that the whole volume of the particle has the analytes have access to it. So if we actually look at a schematic chromatogram, what we will have a V0 value. So if I actually injected a compound which was bigger than my pores, it would have no access to the pores, and it would pass straight through the column, and it would have a volume of V0 and would look at this in this position. If I do the complete opposite to that, I have a very small molecule in there that's got total access to the pores, then what happens is it will be retained, and it will be retained to this point, VT. And then what we've got is we've got a whole range of polymers that we could actually put down, which have an intermediate elution volume, VE1, VE2, etc. Okay, and what we're going to do is, for example, if we actually, when we calibrate a column, if we want to put maybe a known material down for VE1 and a known material down for VE2 of known molecular weight, then if we inject something between those, an unknown, then we can actually use that as the basis for actually determining the molecular weight, and I'll talk a little bit more about that in a minute. Okay, so we've introduced this term KD, which is the partition coefficient that molecules have to the pores. So we have a couple of equations here, which it's all on, this lecture will be on Moodle. You can have a copy of all these. But in the true sense, then what we really need to do is we need to discuss it in terms of this arrangement here. And but what we can do, as I've said, is that we can actually come up with a new term, KAV, where we actually make this approximation here, that VS equals VT minus V0. And I think basically what I've said to you there, this KAV, the proportion of pores available to a molecule. We've spoken about total exclusion, total inclusion, and when you come to those situations, then KAV is 0 in this instant and is 1 when it's totally included. You probably just need to get your head round some of those terms, but it's very logical in terms of this distribution into the pores. It's only based on the volume of the pores. And we can come up with a term like this if you actually substitute some of the values into the equations that I've given you. That's the basic equation that we're working to, and that's what we need to recall. Okay, so what I've got here is just a slight sidetrack. We're still talking about the elution volume, but this is, as it says on the scheme, idealized data. Everything I think we've said to you so far, we actually have a physical detector at the end of the column, which actually determines the amount of material coming out the column. Often what happens is when you use the large column that I've just shown you, what you tend to do is it tends to run down under gravity, and often you don't actually have a detector. All you actually do is you just collect fractions. So for example, you might collect 1 mil and then collect another mil, so you do it on a fraction basis. Okay, and then what you do is everything that's coming out the column are in a whole series of different little tubes, and what you'll do is you could actually analyze each of those different fractions for the concentration of the analyte that's in there. Okay, so it could be doing UV vis on it, okay, or you could be doing some enzymic test if you wanted to actually see if this was an enzyme and had activity. You can actually do it that way. But what it really means is you come up, rather than a nice continuum like I've shown before, you have values from the fractions that actually come out the end of the column. Okay, so that's just another form that you use it in if you're using the larger the columns that I've shown down there. Okay, so what I'm going to do now is I've spoken briefly about the importance of separating things and something called resolution. Resolution is a fundamental part of chromatography, and what I wanted to do is just give you an overview of what resolution is. There is no substitute for resolution, incidentally. You talk to any chromatographer, they like to pull the peaks apart because then they can be detected singularly and there's no confounding of the analysis because one is overlapping another. Yeah, and so that's pretty much where we want to go. But there's a couple of equations here. You don't actually need these, but it's more just for completeness because it's such an important component to chromatography. But basically what we've got is we've got two peaks here, and we can actually describe the resolution based on their height, their width at half height, and the distance between them. And we have an equation here which allows us to determine what the resolution is. But in terms of what does it mean in terms of how far the peaks are apart, if you just actually have a look here, we've got a situation where we've got pretty much total resolution. We've got a resolution of 1.5. In this scenario, we have more overlap. They are less resolved, and the resolution is lower. It's 1 in this instant. But really what I wanted to do just in this schematic here for completeness is to actually introduce this equation here, which talks about resolution, R, in terms of N, the number of theoretical plates. Okay, so number of theoretical plates we introduced earlier. The more theoretical plates you've got, the more potential you've got for resolution and separation. That's a good thing to have in your system. And one way we can increase the number of theoretical plates in a column is we can increase the length of it. So increasing the length of your column gives you more resolving power, which allows you to move into a state like this rather than this. But the thing that you have to remember here is that it's this that the resolution is proportional to the square root of the number of plates, or the square root of the length of the column. So although it's nice to you do get an advantage by having longer columns, but it's based on this relationship, a square root relationship. Okay, some data. This is data that's actually, how are we doing? Come off of the SecMal systems that we've got in the lab. And we're very fortunate because we've got a couple of detectors. We've got the viscostar giving us differential pressure. We've got refractive index, and we've got light scattering. So what I've done here, I'm actually using a Puruland polysaccharide. It's 400,000 molecular weight, 400 kilodaltons. I've got a 10 kilodalton Puruland polysaccharide, and I've got glucose. Okay, so a range of different molecular weights there. Some are going to have access to the pores, some aren't. So what we've got here is we've got, if we look at the if we have a look at the refractive index trace, we've got our 3 peaks, 400 kilodaltons, 10 kilodaltons, and then we've got 180 molecular weight for glucose. So this gives you some idea of the sort of resolution that you can get by using our system in the lab. It's a high pressure form. It's got considerably more theoretical plates than the low pressure version, the big column. And in addition to the refractive index, we've got light scattering. You can see the large polysaccharide scatters a lot of light. They're in there at a roughly equi-concentration, by the way. The smaller molecular weight scatters less light, and glucose doesn't scatter any light. In terms of the viscosity trace, you can see we've got a similar situation here, except for the glucose does have a finite viscosity change. So that's the sort of data that we actually work with. All this stuff up here is a consequence of how the viscostar works, and you don't really need to worry yourself about it. The chromatogram effectively finishes here. That's what we're interested in. Okay, so we've described KAV, the average partition coefficient, and what we can do, similar to what I've just said, we can actually run some standards down our column. Let's just say it's the large of the columns here. I can plot a graph that is log of the molecular weight of my standards against the KAV that we see, and I can draw a line like that. And from that calibration curve, what I can do is any unknown molecule between these molecular weights I can actually put on my column, and what I will do is I will get some KAV for it, and I can follow it across here, just extrapolate it up and come across, and from that we can actually go back and yeah, we can calculate KAV from the volume terms, and then we can work out what the molecular weight is. So we would be calculating VE, we would work out KAV, it would come to somewhere like this, and we would extrapolate across, and then we could work out what our molecular weight was by the calibration curve that we've got here. Okay, so there's a couple of things, a couple of slides that I'm going to go through here now, which just sort of give you some idea of the sort of scope of GPC phases that's available to you, and it's just some reasonably obvious statements, but we can, I think I've already said, column size, you've seen large ones and small ones, analytical and preparative, that's what we tend to call them. In terms of the phases themselves, most of the phases are reasonably inert to solvents, so we pretty much can take any solvent, but you can have polar ones and non-polar systems. Okay, but as far as the matrix is concerned itself, that is the component that's most important. And there's a whole series of materials, there's a whole series of range of particle sizes and pore sizes. And all those, when you actually choose a column, you choose it by design based on the molecules that you're wanting to try and separate. So here's some names of some typical gel permeation phases: cephacryl, cephadex, cepharose, superdex. They're all trade names. They all do slightly different things, but I've just highlighted one particular one, cephacryl. A whole range of different designations in terms of the size. This is trade names that companies tend to use. You can actually get on and you can type some of these names in, and it will show you what particle size you can get, what the structure of the matrix is. But basically what we find here is that we've got proteins and dextrans, and you'll actually see there's a difference in terms of the molecular range that they're applicable to. And this is because what we find is that we can analyse higher molecular weight proteins because they tend to be more compact, more spherical and globular, and therefore the range is represented by that. And then for dextrans, they tend not to be like that. They tend to be more open form. Size and shape matters. They have less access to the pores, and hopefully you can understand the logic of the series that I've represented there. Yeah, a good question that could be posed when we're doing this sorts of analysis is, okay, I understand the column, I understand the flow, but one thing that I need a little bit more information on is how much material do we put on the column? Okay, now everything we've spoken about so far has been in terms of volumes, and this slide really just tells us that we need to have an injection volume that's something between 0.5 and 5% of the total bed volume. Yeah. Right, okay, and there's just a couple of things that you can read through here. Don't really need to say too much about that. Okay, but I think the only thing really I suppose I should emphasise at this point is the effect of flow rate. We've spoken about it already in the context of general chromatography, because don't forget we're trying to strike a balance between longitudinal movement and radial interaction with the bed. So in terms of trying to improve your conditions, one thing that you've got available to you is the flow rate. The lower the flow, the more radial diffusion you get, the more interaction with the bed, which is a good thing. But the problem with that is if the flow is slow, peak broadening comes into play, diffusive effects come into play, and rather than the peaks being reasonably sharp, they're quite broad. If you have too high a flow, you don't get so much peak broadening, but you don't get so much interaction with the bed, and therefore the peaks, rather than being separated, are close together. So they're the sort of optimization things that you can do. Okay, so coming to the end, I talked about GPC this morning, and I put it in the context of general chromatography, but there are some other types of chromatography that might be relevant to biomolecules, and we've got a couple here: ion exchange chromatography, hydrophobic interaction chromatography, and affinity chromatography. All these things, they have a different mechanism by which the analyte interacts with the stationary phase. Everything we've spoken about this morning has been size and shape. Ion exchange chromatography is where we actually have a charge attraction between the analyte and the stationary phase. And incidentally, one thing that you might consider is when we work with GPC, we just have a standard mobile phase running through our column. We don't change that mobile phase, it stays constant. A lot of chromatographies, what you actually do is when a molecule actually absorbs onto the surface and is held on the stationary phase, what we can do is we can actually encourage that to move. And we can encourage it to move by changing the solvent strength. Now, what we do with all these types of chromatography, because we have a chemistry going on, we actually can change the solvent strength of our mobile phase. And a great example of that is when we're working with HPLC, maybe reverse phase, for example, what we'd have is we'd have a typically binary gradient. And that binary gradient means we've got two types of solvent in there. One is a strong solvent, one is a less strong solvent. And what we tend to do is when we inject our sample onto the column, we inject it in the weak solvent. And what happens in that scenario is all the molecules want to find a home on the stationary phase, and they're held up. Okay, now I could actually continue to pump that weak solvent through my column, and they wouldn't move very much. They would take ages to come out. Okay, they're the molecules that are bound. The molecules that don't have a high affinity will actually go through the column, and you can see those. But that's the problem. What you sometimes have is you have peaks coming out the end, and you've still got some material on the bed. But what you can do is you can change the solvent strength by changing the ratio of your solvents. And you, for example, in reverse phase, you might inject in water, and then what you would do to try and move your molecules through the column, you can actually increase the amount of methanol in your system up to 100% methanol. And what that really does is it allows you to have, if you've seen a HPLC chromatogram, got lots and lots and lots of peaks on it, because you've got this capability to change solvent strength. We don't have any capability to do that in GPC, because it's we use the single concentration mobile phase. It's all based on size and shape. And the consequence of that is that we tend to have one or two very broad peaks, pretty much what I showed you in my data. If you've seen chromatograms from the literature, you would have seen many, many peaks coming out. So the chromatography, depending on the type of chromatography, depends on the form of the chromatograms that you get. So there's just 3 types of different chromatography that's available. Okay, and I'm not going to tell you what that is. So that's gel permeation chromatography. Hopefully you understood the basis of what we're talking about there. And I don't know, it would be nice if you get some opportunity to come across it. Don't know whether it will be within this course, but I mean, we do run our columns, and if you're around and it's running, I can show you basically the output that we're getting and how we process it.